All right, team, buenos dias. We're back with FRQ number 2 from the 2026 Mechanics AP Physics C exam. As with the last one, if you want to see the actual question, it is linked in the description on the actual College Board website. So let's get into it. In this one, we have a projectile being launched, and then it goes boom at the top of its trajectory. Our first mission is to draw the momentum diagrams for these. So they tell us that our horizontal and vertical components of the momentum vector are represented by a figure that they give you. So in the original figure, since I don't have the question here, they give you px of the original guy. He's 4 boxes tall. And our py is 2 boxes tall. And they want us to draw the momentum diagram at t equals t1, which is at our max height. So when we're at our maximum height, that velocity in the y direction is 0, which means our momentum in the y direction is 0, which makes sense because we have an external force in this case. That's going to be gravity. Gravity is the reason we slow down on our way up. So momentum is not conserved in the y direction. It is, however, conserved in the x direction, and that's how we're going to draw this picture. So that original 4m mass goes boom, and it turns into q and r. So px is conserved because there are no forces in the x direction. We only have gravity. And then whatever internal force caused those things to explode. Internal force, emphasis on that. So the momentum that I start with, I'm starting with 4 boxes. I'm starting with mass, 4m, times my x component of my velocity. So v naught cosine of theta. I'm going to go ahead and write that out now because it's going to help us later when we have to figure out some different pieces. So my initial momentum, I've got my mass 4m. I got the horizontal component of my velocity v naught cosine theta. And then I'm going to burst into piece q, who has a mass of m, and piece r, who has a mass of 3m. Now, they tell us, I'm going to write v1 and v2 for right now. So they tell us that piece q is going to end up back where it started at x equals 0. So projectile motion is really fun because mass does not affect projectile motion. It doesn't affect the time. It doesn't affect the max height. Well, like in the kinematic equations anyway. So piece q goes back to where it started. So that tells me if my initial velocity was v naught cos theta to get up to the top, my initial velocity to get back down to where I started is going to be v naught cos theta, but in the opposite direction. So his momentum after the crash is going to be minus v naught cosine theta because he's going to the left back to where we started. So I can actually figure out the final velocity of that second piece, that piece r, from my conservation of momentum. And it turns out that this is going to be what you need to do in order to draw your graphs for part A and part C, which is why I'm doing it here. Okay. So if I notice my initial momentum for mv naught cosine theta, piece q is mv naught cosine theta. That's 1/4 of the initial momentum, but in the negative direction. So I started with 4 boxes. 1/4 of that is 1 box, but in the negative direction because we're moving to the left now. So he's going to be 1 box down. Now momentum needs to be conserved. So if he's going to be 1 box down, that means r, in order to get a total of 4 boxes, needs to be 5 boxes up. So 1, 2, 3, 4, 5. 5 boxes up. Boom. There's our momentum diagram. So momentum in the x direction has to be conserved. Momentum in the y direction is 0 because we're at our maximum height. Now, I'm going to continue on with this conservation of momentum just to figure out how fast piece r is going to go because it's going to help us for the next part where we have to figure out where does it land. So I'm going to add this piece to the other side. So I'm going to have 4 mv naught cos theta. I'm going to add that mv naught cos theta over here to get a total of 5 mv naught cos theta is equal to 3 mv2, which means my final velocity is going to be 5/3 v naught cos theta. Okay, so there's our diagram. Cable neta, momentum conserved. In the x direction, we've got 4 boxes to start with. We've got -1, +5, 4 boxes to end with. We good. Okay, part B. We want to derive an expression for x2 in terms of v naught theta and physical constants as appropriate. So x2 is where piece R lands with respect to where we launched it at x = 0. Now, this is where I wanted to use my conservation of momentum fun times. So I'm going to rewrite that down here. Just because that's probably going to end up being part of something that we need to show for some points. 3 mv2. This came from conservation of momentum. There's my mv. Sweet. So doing some algebra again. Blah, 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 blah. That means v2 is 5/3 v naught cosine of theta. Okay, sweet. So we want to figure out how far away piece R lands from the original projectile. So as a refresher, it goes like boop. It goes like boop. Piece Q comes back and lands at x = 0. Here's piece Q. Piece R is going to go and land over here at x = x2. x1 is that location where they explode. And yeah. So there's actually 2 ways that you can do this. So you can either figure out how far it goes on the way up using projectile motion, separate, figure out how far it goes on the way down using projectile motion and this initial velocity at the top after conservation of momentum. Or you can use center of mass principles. So we are actually going to look at both. Cool. So I did it the center of mass way. So if we have things exploding, the center of mass isn't going to change the original trajectory that it wanted to do. So our center of mass is still going to follow that initial, I want blue. So our center of mass is still going to follow that initial trajectory where my initial velocity is v naught, and then I carry about my business, and then my center of mass is going to land down over here. Okay? When I explode at the top and piece Q comes back over here to the left of where it's supposed to be, that means piece R is going to go over here somewhere to where x2 is at. There's my piece R. Okay? Personally, I figured out how far does it go to the center of mass. We know the difference, like we know where piece Q landed, so we can figure out where piece R landed. Let's do it that way. So from my handy dandy projectile motion equations, we know that our vertical displacement goes like v naught t minus 1/2 gt squared. Our displacement from the beginning to the end is gonna be 0. So that vertical displacement is 0. That vertical velocity is v naught sine of theta t minus 1/2 gt squared. So that means that v naught sine theta of t is equal to 1/2 gt squared. One of those t's cancels out. And then if I multiply 2 over and divide by g2, v naught sine theta over g is how long it takes to get all the way to the other side. Now you'll remember that my horizontal displacement goes like v naught x times t, because there is no acceleration in the x direction. So that's going to be v naught cosine of theta times the time it takes to get all the way to the end, which is that 2v naught over g sine theta. Now this is where my center of mass lands. So that's where my x center of mass is going to end up landing. That's going to be at 2 v naught squared sine theta cosine theta over g, just to kind of clean it up a little bit. So center of mass, that's where that's going to land. So if you want to use center of mass, remember that your center of mass goes like, hey, where is the first thing times the mass of the first thing, plus where is the second thing times the mass of the second thing, and then divide by the total mass. Well, we know the center of mass is going to end up at 2 v naught squared over g, sine theta. So we know the center of mass is going to end up at 2 v naught squared over g sine theta cosine theta. So we know where our center of mass ends up. Our first object, Q, had a mass of m. He had a mass of m. He ended up back where we started, though, where x is equal to 0. Nice. Mass number 2 is mass of r, which was 3m. And where are you? x2 idk. Let's find out. And our total mass is m plus 3m, or 4m. So I've got 2 v naught squared over g sine theta cosine of theta. I've got a 3m x2 up top. I've got 4 m's on the bottom, multiplying by 4/3 to the other side. That gives me 8 over 3. That's an ugly 3. That gives me 8/3 v naught squared over g sine theta cosine theta is where x2 ends up being, using center of mass principles. Nice. All right, on the other hand, if you wanted to figure out using just projectile motion, you can figure out how long it takes to get to the top. So that's going to be half of this time. So t to the top, t top, is going to be v naught sine theta over g. If I just plug that back into my displacement, that's going to give me x1 is v naught cosine theta times v naught sine theta over g, which is v naught squared over g. I like putting sine first. Don't know why. I just do. Sine theta cos theta. So that's how we get over to x1. So then for the second part of the trajectory, we know the speed that we start with in the horizontal direction. So that's our v naught in the x direction. So that's our v naught in the x direction. That's going to be 5/3 v naught cos theta. See, I told you that conservation of momentum is going to come back. Times t. So I need to figure out the amount of time it takes to get back down. So the fun thing is that the amount of time it's going to take to get back down is the same, because it only depends on my initial velocity in the y direction and gravity. The initial velocity in the y direction is 0 in this case. We're falling the same height as we went up, so that's the same. So that time to get to the top is going to be the same as the time it takes to get back down, even though we have different masses and different horizontal velocities. So that time is also going to be v naught sine theta over g. So this is x1 to x2. So that's where we get 5/3g v naught squared sine theta cosine theta. So x1 is how long or how far it is to here. X2 is how far it gets to here. So I'm going to add those together. So 1 stuff plus 5/3 stuff. So 3/3 plus 5/3. I also get 8/3. Phi naught squared sine theta, cosine theta. So I get the same thing, whether I decided to split it into 2 separate projectile motion equations, or if I wanted to utilize the center of mass. The center of mass does not change what it wanted to do from its initial trajectory, okay? So that's actually how we're going to do our graph for part C. Now, that's the reason I did the center of mass, is because we're taking into account that the center of mass in the x direction, there are no external forces in the x direction. So my center of mass, velocity, in the x direction doesn't change. So I'm going to put a nice horizontal line. Keep doing what it's doing. Velocity in the x direction, center of mass. Now, they told us already what was happening to Q. They literally told us in the problem that Q is going back to where it started. So that means, remember that your area under graphs, so area under a velocity versus time graph is your displacement. So that means the displacement of part Q is 0. So same time up, same time down. So this is going to be the velocity of Q. He's going to go negative v in the opposite direction. Boom. Now we figured out in the last part that the velocity of part R is going to be 5/3. So he's going to be like there. A little bit higher than that in the x direction. And remember, it's in the x direction. There is no acceleration, so these are all horizontal lines. All right. Okay, so for part D, now we have a situation where we're launching the same initial conditions, so same angle, same initial velocity, blah, blah, blah. We're still going to blast into parts Q and R, but instead of Q coming back to where we started, Q is going to drop straight down. So here's where Q is going to end up landing. Where is R going to land? Is it going to land at a point further than its original location, x2, or is it going to land closer? So in this case, we want to look at it from a conservation of momentum perspective, and I'm actually going to type this one because it's a lot of words. So if the x component of the velocity, of piece Q is 0, because it is dropped straight down, then it has px equals 0, no velocity, no momentum, which means all 4 boxes of initial momentum, if you want to tie it back to your bar chart, get transferred to piece R. So piece R has 4 boxes of momentum after the explosion, while piece Q has none. Now, you could also talk about, in the original case, since Q ended up going backwards, it had negative momentum after the explosion. So R had to have extra positive momentum to compensate and conserve px. So in this case, since Q has 0, I know, R has less px than in the first case. So it will not go as fast, and thus it will not go as far in the same amount of time it took to fall from the same height. We're getting to the same height. So it's highly likely you may have to specify that the time to reach the ground is the same in both cases, which means that the velocity that you leave that explosion in matters. So you need to talk about the time it takes to get back to the ground is the same in both cases. So the velocity that piece R is leaving that explosion being smaller because of the momentum conservation means it's not going to go as far. All right, that's it for FRQ number 2. Yes, this is number 2. We're going to hit up with the experimental design question next, my favorite, because it's the easiest one to get points. So hopefully you got some points on this one using your conservation of momentum and projectile motion. Fun times. See you in the next one.